distressed.
Okay.
Okay, hello everyone. As usual, I start with your questions. Do you have any questions about the homework that I hope you guys are doing?
I have one.
Please
No,
put
you
it
go
on
ahead.
chat. What?
I was talking to the other guy. I asked him to go ahead with his question.
Okay, put on the chat. You guys can put both on chat, so don't worry. I can read both.
Okay.
Get going. Okay, number 27, particularly the row reduction. Okay. Anybody else? So I will pick up this problem. I mean, I will look at it actually and do it. So before, I would like to ask you those questions, which are already from the homework. And I think that's section 1.2. I want quick answers. They are not hard, but I always want to bring you back to system because you have to have total understanding of those. So this is problem number 24 in your book. And the question is, suppose a system of linear equation has a 3x5 augmented matrix whose fifth column has a leading entry. Now, the book is using pivot column, but to make it really simple, it means it has a leading entry. Is the system consistent? Yes, no, and explain. So whenever you have this kind of problems, usually my advice to you is just draw the matrix, the echelon form of the augmented matrix, and then try to answer the questions accordingly. So you have a minute to think through that. Okay. All right, I see Bryce is answering non-consistent. Do you agree with him? Inconsistent. Chris also? Yeah, absolutely inconsistent. And let us see the picture. Always try to draw a little bit because it helps you. 3x5, 3 equations. And 3x5 augmented matrix, it means the augmented have 3x5. It means the original system is 3x4, 3 equations and 4 unknown. And fifth column has a leading. It means we have a leading here. That's the picture. System consistent? Absolutely not. If there is a leading, it means we have a bunch of zeros. So always, I don't care about anything else. I'm done here because that's the reason. So the last row will read, this one reads 0, x1, 0, x2, 0x3, 0x4 equal a non-zero number. It means if you try to solve the original system, I end up with something that doesn't make sense. It means there is nothing that will solve the system. All right, another question is again from your note. What do you need to know about leading entry in an augmented matrix in order to know that the linear system is consistent and have a unique solution? That's number 28 in your homework. Always imagine the matrix, what's really going on, and what should happen. So we want it to be consistent, and you want to be a unique solution. So imagine a scenario for, let us say, a 3x3 system. Then I want you to imagine a scenario for a 3x4 system. Okay, imagine the scenario. If you want consistent and you want unique, what should happen? Then take a 3x4. 3 equations. No, sorry, I meant 4x3. My apology. 4x3. And ask yourself what could be. There are no leading entry in the final column. That's not enough. That will guarantee consistency. Okay, so one of your classmates said no leading in last column. In the last column of the echelon form of the augmented. Let's get that very clear. Okay, that's half of the story. This will guarantee what? This will guarantee only consistency. But they want unique. What will guarantee that the solution is unique? So I will read Adam tell me there is only one leading entry per column. That's absolutely correct. So to have a unique solution, I don't want any free variable. I only need basic variable. To avoid free variable, it means every column should have a leading except the last column to guarantee consistency. Okay, so no free. So the answer should be every column should have a leading except the last column. So if I have a 3x3 matrix, and then we'll write it clearly. So a 3x3 system, it means I need everywhere except here. No free variable. H1 is basic. I can solve for it. I can solve for that. No question. I can solve. I can solve. Even if I have a 4x3 system, 4x3, then again, no free variable here. Unique means this should be leading, this should be leading, this should be leading, and no leading here. So we should have, this is the picture, no leading, and you have to be very careful. So the answer is, as one of your classmates is, the answer should be every column except the last one, every column except the last is a leading. The last one has a leading. That's what will guarantee the uniqueness and the consistency. Okay. Right, so these are questions that I expect me to answer. The question, I always ask you questions along those lines. What will happen in this scenario? What will happen in this scenario for the system? All right, so this is the beginning. Now I'm going to look at number 27. We look at it very quickly because we have a lot to talk about. So number 27, I forgot what is it about. Okay. So I will read 27, the best here, and then we do the math. All right, so a mining company has 2 mines. One day's operation at mine 1 produces ore that contains 20 metric tons of copper and 550 kilograms of silver. So we have two mines. Now, mine 2, number 1 produced that many tons of copper, that many of silver. 1 day's operation at mine 2, it produces 30 metric tons of copper and 500 kilograms of silver. And then, they have data. They use vector to basically introduce this data. So V1 has 2 entries. The first tells me in mine 1 how much copper they produce, mine 1 per day, 550 how much silver they produce per day. So they used vector to say the data, what's really in it. And V2 tells me the first entry, how much ore mine 2 produces a day, and how much silver mine 2 produces per day. So then V1 and V2 basically represent the output per day, as simple as that. And the question is, what physical interpretation can be given to the vector 5V1? So 5V1 is going to basically represent the output in, so 5V1 means the output in mine 1 for 5 days. Because 5V1, it means you multiply this by 5, the first entry, the second entry. This tells me basically in 5 days, what's the output in mine 1. Now, B, suppose the company operate mine 1 for X1 days and mine 2 for X2 days. So we do the following. Sorry, I need a clean piece of paper. So mine 1 for X1 days, mine 2 for X2 days. Write the equation whose solution gives you the number of days each mine should operate in order to produce 150 tons of copper and that many kilograms of silver. So the question is really, how many days? So X1 represents the number of days. The first mine should produce, and how many days, so that the total output is 150 tons and 2,825. Okay, so if I want this as an output, for how many days I should operate the first mine and for how many days. So the problem is we need to solve the following system. And 3,500. Okay, that's the system. So again, it means basically we add those vectors as we did before, and we set this to be equal to, so I need to solve for X1 and X2. And I will probably not do all of it, but I will just get you going. 2,825. So solving the system is really, I need to set those first 2 entry equal and those 2 entry equals. So doing that, this will bring me to the following augmented. 20, 30, 150, 550, 500, 2,000, 2,825. And your classmate is basically how to go to the echelon 4. So if I am doing it by hand, which maybe I will try to avoid that, but I'm doing by hand, what will be the first thing I will actually do? I probably divide this by 10. I divide this by 10 maybe, or at least the first one, which would leave me 2, 3, 15, so divide by 10. And this one we can keep it. Okay. And then we do the operation. I mean, we do the simplest operation. Then you can take the first row, multiply it by 550 over 2R1, add it to R2, and this would be your new R2. And to do that, you basically get very close. So you get to a 3, you get 15, and then it's just math here. If you take minus 52, so this is going to give me a 0. And then I will not spend the time doing this, and then you proceed. And the end of the problem, basically. And you can solve for x1, and you can solve for x2. Okay? So that's the operation you can do. First, divide by 10 to make things easier. Once you do that, then you take the simple operation. You multiply the first row by 550 divided by 2, it creates a 0 here. Here there is some math you have to do, which is, I don't think it's very hard, and this is some math you have to do. And then you will find exactly what you get. And according to my notes, the answer is going to be, if you really push it, you get 0, 1, 4, 1, 0, 3 halves. That's what you should be getting. Okay, but that's the main one. Once you do this, you can solve for x2, then back up, solve for x. All right? So today we're gonna keep working with linear combination and introduce the idea of a span and finish the idea of a span. So before we do that, I asked you guys to make a copy of this. Did you make a copy of that? Okay, I asked you guys to make a copy of this, to print it.
Yes.
Yes, so please, I want you to use your copy, because this is hard for me to, you take your copy and let us answer the first question. So I want to make sure every one of you can do those type of problems. So I have two vectors, V1, 2, 1. I point them on red, and V2 minus 2, 2 in red also. Then I'm going to ask you the following. Use the picture, nothing deeper than that, no algebra whatsoever, so that you can write each one of those vectors as a linear combination of V1 and V2. Okay, so I basically, as I said last time in class, you pick a vector A. So for example, this is my A. Writing it as a combination of V1 and V2 is actually, you want to go from here to here, following those two directions. And the idea how much you have to go in the direction of the one, how much you go direction of the others. All right, so that's really what the problem. So I'm going to put here 2 lines. Those are the directions we can follow. So they will be very clear for us. And then let's do that. So since each one of you has, I hope, a printout paper, let us get A1, A. So I want to go from here to here. I have 2 roads to follow. So what is A? Quickly. So I can start here. I go. So I seem to be going this way, that way. I'm hitting A. So A is V1 plus V2. Now B. And B, you guys want to do it? I did A just to show you how we do it. B is the vector minus 4, 1. Means if I go, this is minus right here, and 1 right there. So this is my vector 4, 1. And my question is, so this is 4, 1. This is here, and this is here. This is my vector 4, 1. Okay, and my question to you is, if you guys have your own copy, how can you write V1, B as a combination of V1 and V2? So start from here and move along those roads. Minus V2, minus V2. So this is V2. Oh, sorry. Somebody is telling me minus V1 plus V2. All right, let me say I agree. To get here, you have to go in the opposite direction. But then immediately you have to move. So you start this way, then you move. Minus V1 plus V2. Absolutely correct. So we do the last two. C. C is minus 6, 6. So minus 6. And no, sorry, 6, 6. 6, 6. So this is my vectors All right, this is 6. So this is my vector C. Again, we start from here to here. Again, I want you to write it as a combination. So if I want to get from here to here, following the red line, parallel to the red line, how can I go? Anybody? So I want to go from here to here. So it seems that I move. I don't want to write it. I want you to guys write it quickly, please. So I have this route, and we have this one. How can I get to C? 4v1. So I'm going to start, keep moving, keep moving. I cannot go back yet. I will not hit C. I will not get back. I will not hit C. I will not get back. I get back. I hit my C. So again, my C is 4v1 and plus, in this case, v2. So all the vectors, I'm being able really to write them. And finally, I picked -7,4, and I marked it a little bit before class because it's easy for me to see them. So this is -4, and my 6 is right here. So my vector is, my D vector is here. So this picture, I always bring you back to it throughout the semester. That's why I want you really to understand it. So this is my vector D. And now I want D to be written as a combination of those. So I want to get from here to here, only moving parallel to the red line. So any ideas? But just basically, yeah, I'm tracing myself. So I want to get here, from here to here. How can I get? Anybody has any answers? So should I go in the positive direction of V2 or the opposite direction? I want to get here. I cannot go that way. Of course, I have to get to that way. How much? Go. I cannot go back yet. I have to keep going. Almost like that. So, which will give me how much? V2, another one, and a half. So almost 5/2 V2 in the opposite direction. And V1, it seems to be, that's my V1 in here. This is my V1 in here, and this is my V1. So we just follow and ask ourselves. Now you can check. I mean, we may be off a little bit, but that's really what the picture is telling us. So geometrically, almost, as I mentioned last time, but has to be clear, almost every vector in this simple scenario, I was able to write it as a combination of V1 and V2. Right. My second question is, okay, geometrically it's clear. My second question is, how do we show algebraically that if I pick any vector, regardless what the entries are, I can write it as a linear combination? So my second question is really to answer the same idea, but this time I want it a little bit algebraically, not geometrically. So that's geometry, and that's the algebra of it. So what do I mean? What do I want algebraically? And this one I will take it. You guys will do other problems along those lines. So I want to show you that if I pick any vector, I can write it as a combination of the vector V1 and V2. Means that no matter what the vector is, I should be able to show you. It means you have to show the following, that if I take this equation, whether I call those coefficient x1 or c1, it doesn't really matter. So if I take, to have to show that this equation, c1 or x1, those are scalar, times c2, so this is 2, 1, minus 2, 2, equal b1, b2. So that's what we have to show, that this vector equation has a solution regardless what B is. So regardless what B is, what the vector B is. Okay, so to show that B is, it means we have to show that regardless what I pick for those, I can always find the C1 and C2. So it means, what do I have to show? So I have to do the following system. I need to solve this and convince you that the system is always consistent. You have to solve and show you that the system is consistent regardless which entries I put in here. So we want to solve. So it was this last time to solve this. That's really equivalent to do the following. I add, this gives me 2C1 minus 2C2, and the second one, it's C1 plus 2C2 equal B1, B2. Be careful, C1 and C2 are the unknowns. I'm trying to convince you that this is consistent. All right, so doing this, it means we have to solve the following system. C1 and C2 are the unknown in here. So we have to solve this and make sure that we can always find a solution. Okay, how do we do those type of problems? Take the augmented matrix, 2. So we know that this should be V1, so we know what this should be, and we know that should be V2, and this is B1 and B2. Now I have to tell you that those don't matter. Anything will work. All right, so let us solve the system. So we're gonna solve now, because I always like to switch because I like my leading to be 1 if I can. If I can't, I can't. So I switch this to make the math easy for me. But I switch everything, so B2 become here. And now I take the first row, multiply it by the second, add it to the second, and this will be, I take minus 2 row 1, this will be my row 2. Okay, now we do that, we get 1, 2, B2. So that's the algebra why I can always find those constant. Minus 2 plus 2 is 0. Minus 2, minus 4, minus 4, minus 2, that's a minus 6. And finally, I have minus 2B2 plus B1. Please ask questions if you have any issue with that. And now, this is my question to you. Can I always find a solution of my original system? It means, can I always find those weights that will give me minus 2, 2, regardless of what B2 and B1 is? Can anybody argue that? Means, is there any value for the vectors B which will make this system inconsistent? No, absolutely, because that's a leading here, right? And this is a leading. It means the scenario 0, 0, non-zero cannot occur. That's really what's happening in this. So regardless what the value of B1 and B2 here, I'm not gonna have a leading in the last column. I always have a leading in the first and the second. So there is no room for a leading in here, which will give me a consistent system. So let's write this down. This is consistent because we have no row. There is no way, because we have no row of the form, there is no way I can create this row of the form 0, 0, and leading. There is no row of this form. We have a minus 6 here, and we have 1 here. It means we have no form of this row. It means the system consistent regardless what B. It means no matter what the vector B is, no matter what B is, regardless what the vector is, and thus algebraically, okay, we can write B as a combination of the vector V1 and V2. Combination of V1 and V2. Okay, so this is consistent because this cannot occur. I have a leading and a leading, so that's why it is consistent. Therefore, no matter what I put here, I can solve. So if I put for vector V1, V2, 100, 200, I don't care. I can always find a solution. Okay, so now we solve this problem geometrically. We know what to do, and we solve it algebraically. So we were able to see the problem in both ways. Now we're going to move along the same lines, of course, but we're going to introduce the idea of a span of a vector, and then work with this idea most of the hour. So let us recall. B is a linear combination, you guys have this already, of a bunch of vectors. If we can find scalars or weight, such that B could be written as the sum of those vectors with a weight attached to them. That's a linear combination. Now, the new idea is span of vectors. What's the span? Suppose I have a bunch of vectors in Rn. What's the span of V1 through Vk? So the span denoted by, so that's the notation, is the collection of all the vectors that are linear combination of V1 and Vk. Because if you have two vectors, as realized in this problem, I can have a lot of linear combination of them. I mean, and we actually even showed you that every vector is a linear combination. The span is the collection of all those vectors that are linear combination of V1 through Vk. So in words, the span is all vector B. That B is a linear combination of V1 through Vk. So that's really what the span is. Okay, we're going to take first example just to understand the word span, and then we're going to analyze the span of vectors in more details. Okay, so I start with the, can I move on? If I cannot move on, let me know. If nobody complain, I move on. If you complain, I'll stay. Okay, that's better. Okay. So this, stay with us for a moment. All right, can I move? Okay, thank you. All right, so now the first question is to understand the word. So question number one is, let V1 be 1, 2, 3, V2 minus 4, 2. And W is just a vector, minus 3, 0, minus 4. My question is W in the span. What does it mean? What does it mean it's in the span? This means is as simple as that. Is W, it's another way to ask you, is W a linear combination of V1, V2? So asking you, is it in the span, is a different way to ask you, is it a linear combination of V1 and V2? So we don't know if we look at them. Always it means, can I find weight? We can call them as a, such that if I put a little bit of weight on each one of vectors, I can reach my vector minus 0, 3, minus 4. So that's really, is it? So it means, can I do that? 4, 2, okay? So to be able to do that, as we've been doing several times, it means we have to solve a system. So this is really equivalent to solve the system, where this is the augmented matrix. Make sure how you get from here to here, don't memorize. And this. Because if you remember, if we add those at vectors, this will actually give me the following system. C1 minus C2 equal minus 3, and 2C1 plus 4C2 equals 0, and 3C1 plus 2C2 equal minus 4. So it's really this system that I am solving. All right, let's try to do it as quickly as possible because we've done those by now. minus 2 plus 2. Minus 2 plus 2 is a 0. Minus minus is a 2 plus 4, it's a 6. Minus minus, that's a 6 also. Now minus 3 plus 3. Minus 3 plus 3, that's a 0. Minus minus, that's a 3. Plus 2, that's a 5. Minus minus, that's a 9. Minus 4, it's a 5. So we have to solve. Usually, as we said several times, solving, you have to get to the echelon form. This is not in echelon form, so we can't stop yet. So we probably go one more further step, and you should see what's really going on in here. Now, I don't like the 6. You don't like the 6 either. So I'm going to divide by 6, which gives me that. And I can divide by 5, the third row. And this will give me this one. Yes, so the numbers are easier if I can. If I make my life harder, I don't do it. Now, my last step, because everything below the leading has to be 0, I need to take minus 2R2 plus R3 into R3, because I need my echelon form. And this would tell me, get me there. 1, minus 1, minus 3, 0, 1, 1, and now we saw minus 1 plus 1, it's a 0. Minus 1 plus 1, it's a 0. So what does this tell me? First, the system is consistent. Crucial. It means I can find the weight C1 and C2. It means I can write my vector W as a linear combination. And this tells me what are the weight. So if I solve, I get C2 is 1, because this equation reads C2 is 1. And actually I have one solution. And the first equation will read C1 minus C2 equal minus 3. So it means now when I solve, C2 is 1 and C1 is minus 3 plus C2, it means is equal to minus 2. What does this tell me? It tells me that the vector W is in the span. So the vector W is in the span, and it tells me that actually it's a combination. It means it's minus 2 times V1 plus V2. It means W in the span. So that's what it means. It's in the span. It means nothing more than, is it a linear combination? Okay, so that's really the meaning of the word. Now let us a little bit understand it more, understand the concept a little bit more. Okay. So while you guys are finishing, okay, let us start grasping the concept somewhere. Okay. Can I move on, guys? Can I move on? Yes, thank you. So now we're going to do the following. We're going to start, as I said, to understand the span. So I'm going to start with the following. Before I do that, there is a terminology that bothers students, and for good reason, which is the following. The book uses, a lot of book use it, is, so suppose I tell you the vector U, the vector is on the line, L, for example. What do they really mean by the vector on the line? What they mean is the following. It means the tip of the, because all our vectors start at the origin, U is on the line L, it means basically that the tip of U on the line. So the book uses that, and on the line L, all right? So if I take supposedly a line here, so, and I take this vector, this is my line. This vector is on the line because all my vectors start at the origin. So really what defines my vector is really the tip. So this vector is on the line. However, if I draw this one, this is not on the line because the tip is not on the line. So that's really what they mean a vector is on the line. Right. So now let us start working with the span. So the first one is we're going to work with the span of one vector. What's the span of one vector? It's going to be fairly simple. So span of one vectors, and whether the vector is in R2 or in R3, in this particular scenario, it doesn't really matter which one you take. Okay, so suppose I have a vector U, which is U1, U2. So I try always to have a picture in our head because pictures help. So this is U, this is my U. I don't have to pick it in the first quadrant, I can pick it anywhere I want. So what is the span of U? What do we mean by the thing, span? Okay. What's the definition? It's the collection of all the vectors that they are linear combination of the vector U. Now I have one vector. So what do I mean linear combination of the vector U? It means all the vectors of the form. What form? Combination of U. What does it mean combination of one vector? It means of the form a scalar times U. So what we mean by the span of U, it means all the vectors which are of the form C times U, C is scalar. If you have two vectors, it's C1U plus C2V. If I have one vector, it means everything of the form C times U, where C is a scalar. So if I ask, for example, let us find 5 different vectors in the span. So 5 different vectors in the span of U. Okay. So what do I mean by that? Simple. It means 5 vectors of the form a scalar times U. So 2U. Basically, you're scaling it. Minus U. 3U. And so on, half U. That's what are the vectors in the span. And there is one which is very important, which is very important that I want? And the zero vector. Is this in the span? The zero vector. Can I write the zero vector as a scalar times U? Can I write it as a scalar times U? I can write it as 0 times the vector U. That's my scalar. Okay. So what's the span of U geometrically? Geometrically, what's the span of U? It's my vector U. What's the span? Every scalar multiple of it. So if this is my U, 2U, 3U. I mean, basically, you're asking all the vector that you can get to by following the direction of the vector U. As simple as that. Minus U, minus 2U. So you can visualize the span as nothing more than the line, this line. Okay, so we can visualize it exactly like that. What's the span of U graphically? So the span of U are all the vectors which are on this line. So the span of U of one vector is nothing more than all the vectors on the line. Which line? Which line? How are we going to describe the line? On the line which is contain the origin and contain U. Now, that's confusing. What do I mean it contain U? It means contain basically the tip of the vector U. That's really what they mean by contain. Okay, so the span of U is nothing more than every vector on this line. Not this one, not this vector, not that vector, every vector in here. And this vector, we give it a name. Sorry, this line, we give it a name. So this line here, okay, we call it sometimes, this line, sorry, is called the line spanned by U. Okay, so when we refer to the line spanned by U, we refer to this line. So geometrically, what's the span of U? All the point here that you can get to from the origin by following one direction, which is the direction of U. So all the points you can reach to by following one direction U are only the point on this one. So span of one vector is actually not hard. Okay, so we can move on. What's the span of two vectors? So the span is a lot of vectors, not one, not two, not three. I mean, it's 2u, minus u, 3u, and so on. It's a lot of them, but all of them have their tip right there on this line. Now what about two vectors? What's the span of two vectors? Yeah, exactly. Except in one case that we're going to take. So now span of two vectors and in R2, and then we take it in R3. Then the span will be clear. So span of two vectors and in R2. Okay. So suppose I take two vectors and I started with a small activity because I want to actually use it as a as my example. So suppose I take the following two vectors. Let's U to be the vector 2, 1. And V, my memory is minus 2, 2. Okay, so we take two simple examples because all the examples are the same. So what is the span of UV? The definition is all vectors, not one, not two, infinitely many of the form. That's what the span of the form. Some certain weight you put on U plus another weight you put on V. Everything of this form. Okay, and that's really what the problem we did at the beginning. So example of vectors in the span, 2U plus V, minus U, minus 2U, and so on and so forth. V is on the span, 2V, the zero vector. There are tons and tons of them. So this problem is what we did at the beginning of the hour. So I took my vector U here, and my V was somewhere in here. And what's the span? Everything here on this line is in the span because it's scalar multiple of U. Everything here is on the span, scalar multiple of V. Everything here in the span because, as we said at the beginning, we can get to. Anything here is in the span. We can go backward and then we can move here. Again, that's why I can go a little bit like this, then a little bit like that. So if I pick any vector here in R2, I can get to this, I can get to by using Q and V. How are we going to express this idea? So every vector in R2, and we did that using the worksheet. I convinced you if you pick any vector, B1, B2, we can find scalar even algebraically so that the vector could be written as combination of U and V. So every vector in R2 is a linear combination of U and V. Anyone? How do we express this mathematically? We write the following. And this way of writing, I wanted to make clear. We write that the span of U, V in this particular scenario is equal, watch the word equal, R2. Okay, so what does it mean when I say that the span of UV equal to R2? This means the following. If I take any vector in R2, if I take any vector in R2, I call it B1, B2. So if I take any vector in here, then we can find C1, C2, such that B is C1U plus C2V. Okay, so saying that the span equal R2 means you give me a vector, I can give you the weight. And that's what we did in the first worksheet. We saw that regardless what V1, V2, we can actually solve the system. And mathematically, we write this is equal to R2. Now, there was nothing special about my vector U and V. There is one thing which is special, which I will point out in a minute, and then we can generalize this idea. So I'm going to ask you the following question. I will keep this on the board. So example number whatever. Suppose I take the following example, or the following question. Let U be question number 2. So let U be the following vector now, or let me call it V1 instead of calling it U. Suppose V1 is equal to 2, 1. And V2 is 4, 2. Okay. And my question addressed to you is the span of V1, V2 equal to R2? Or what's the span? Okay, the question is addressed to you. I want you to think a little bit about it. I want everyone to think about it, and I'm expecting some kind of answer. Draw a picture, do anything you like, and try to understand the problem here. So for this one, I want you first to think geometrically a little bit, and then we think about it more algebraically. So Adam is answering me. Let me see. Let me read Adam. No, aren't they parallel? Same line. Is Adam correct? What is Adam telling me? Absolutely. What Adam telling me is the following. Watch V2. V2 is nothing more than 2 times V1. Okay, so in this class, instead of using parallel, I would rather use that they are scalar multiple of each other. Okay, so V2 is 2V1. So if I go back and check this, so V2 is, so this is V1, V1 is 2, 1. That's my V1. And V2 is nothing more than twice. So this is V1, my V2 is twice that much. That's my V2. So when I start taking a combination of V1 and V2, I can basically never leave this line. Because the idea of a combination, it means I'm looking for all the vectors that I can reach following the direction of V1 and V2. But V1 and V2 have the same direction. So there is no way I can really reach this. Okay, so in this case, the span is definitely not R2. So is span? No. Absolutely not. The span is actually nothing more than a line because they are scalar multiple of each other. So the span here is the line through the origin, is this line. Through the origin, it means it goes through the origin, that contain either U or V1 or V2, I don't care which one you say, that contain V1. It means the line through the origin which contain the tip of V1. Okay, so if you have 2 vectors in R2, this is the issue. So if you have 2 vectors in R2, that's really the picture in general. So suppose you V vectors in R2 in general. So if U and V are not scalar multiples, which is what you guys understand the idea of parallel to each other, if U and V are not scalar multiple of each other, then the span is basically all of R2, meaning every vector in R2. I want this writing to be make clear. It means everything in R2 can be written as their combination. It means if I take any 2x1 matrix, I can write it as the sum of scalar multiple of U plus a scalar multiple of U. That's really what I mean. Any 2x1 matrix could be written as a combination of those. Now, if U and V are scalar multiple, then the span is just a line. So we can, is a line. And we said which line it is. So that's really what happened for two vectors in R2. That's really the picture. The last, not the last thing, but now we're gonna move a little bit to R3 and take vectors in R3 and try to really visualize what's the span of two vectors in R3. And by now you have to move up with me a little bit in dimension. So, case of two vectors in R3. Oh, it's not gonna be hard. If you understand R2 very well, understanding R3 will not be hard anymore. So, span of two vectors in R3. Okay. I'm going to start with two fairly simple examples, with two very simple vectors, and then another one also simple. But okay, so example number one for those. Suppose I take the following two vectors. So let me take U to be one, 0, 0. And V to be the vector 0, 1, 0. So those are vectors in R3. Okay. And let us in R3, it's the XYZ plane, of course. But the book doesn't call them XYZ plane. They call the X1 is the X1 here, and this is X2, and this is X3. Okay, so that's really how they label them. And U is 1, 0, 0. So you go 1 unit in this direction and you stop. So this is my U, which is for those who are doing physics or whatever, 261, this is the I vector. And V is the unit vector here. So that's my V. Okay. And now my question is, what's the span of U and V? It means what are the vectors that I can get by combining those two? So think about it for a little bit. What's the span of my vectors? So basically is every vector, or vectors of the form. So I'm just writing for you to think. A scalar times 1, 0, 0 plus a scalar times 0, 1, 0. So that's really what the span. So geometrically, what is the span? So it's every vector that we can take U, stretch it a little bit, and then after stretching it, move in the direction of V or 2V. That's a vector in the span. So who would like to describe the span? It means if I take any vector which is a linear combination, what can you say about this vector? Where this vector is gonna be? Ideas? So if I take U, that's the 1, 0, 0. I take V, 0, 1, 0. Then I start taking the linear combination. I get a vector, a new one. Where is this vector? Isn't it all numbers contained in R2? We know we are in R3. So I will not accept. Every vector now I have 3 entries. So my vectors are in R3. I'm done with R2. So I want you to be precise in your language. Because when I'm combining those two, I'm ending up with a third vector. But this third vector is in R3. It has 3 components. But what characterizes this vector? What can you say about this vector? If I combine those, what do I get? What's particular about this vector? This component is 0. This component is 0. It means this will have to be the 0 component. And this one is basically C1, C2. So every vector is a linear combination of those two. Its third component will have to be 0. So the span is all vectors of the form C1, C2, whatever number those, and the third component is 0. So what is the span geometrically? It means every vector which is in the x1, x2 plane. Every vector which is in the x1, x2 plane. So it's a plane in R3. In this particular case, it is the x1, x2 plane. It's not R2. It's every vector which is in this plane. So what does it mean in the plane x1, x2? It means the tip of it is in the x1, x2 plane. So the span here is all vectors in the x1, x2 plane. Remember, those vectors are in R3. It means all vectors in R3, actually, let me write this clearly, in R3, mean they have 3 components, but their tip is in the x1, x2 plane. Okay, so sometimes we say that the span is just the x1, x2 plane, but the x1, x2 plane, which is in R3, not this x1, x2 plane. It's the x1, x2 plane that lives in R3, not the R2. Okay, so it's just a plane in R3. Now, let us take a similar scenario. Instead of taking 1, 0, 0 and 0, 1, 0, let me take just any 2 vectors. So let's do that. Suppose I take the following vectors, U. So another example. Should be our last one. U to be the vector 1, 2, 3. And V the vector 3, 4, 5. Okay. And the question is how we can visualize the span of U and V. It means, how can I describe all the points that I can reach from the origin by following the direction of U and V only? Okay, so again, a little bit the geometry here. So these are my places. I am in R3 and I have my 2 vectors, 1, 2, 3. Those I will cheat. So this is 1 vector, 1, 2, 3. And this is my other vector. So I showed them with positive component for the picture to be easier. 1, 2, 3. So this is the origin. This is the tip of that, and this is the tip of this. So what is the span? It means, what are the vectors? So what are the vectors that have the form a scalar times U plus a scalar times V? Where are they geometrically? So we're really doing now the geometry of it. These are the vectors that I get in the following way. I'm starting from 0. I go a little bit this way, and then I move a little bit like this vector here. So those are all the vectors. Or I can move in the opposite direction. So how can I describe those vectors? Let us think about it a little bit. Let me take the following plane. The plane that this plane, and I'll describe it in word. What plane? Okay, so you have to see that the picture is lifted. So let P be the plane that contain 0, U, it means this point, and V. When I say V, it means it contains the tip of V. So 3 points, those 3 points definitely form a plane. And now, what's going to be the span? If I take a vector starting from U, stretch it. By stretching it, I stay within this plane. So imagine this plane. The plane contains the 3 points. The plane will contain everything in U, and this plane will contain V. So if I take U and stretch it, I am inside. I'm not leaving the plane. Then I move a little bit in the direction of V. I am not leaving the plane. So if the vector is obtained this way, this vector will have to be in this plane. So any vector that I can reach by following a little bit of U, so if I go a little bit of U, I am within it, and I move a little bit, I am within it. The resulting vector is it in my plane. So the span, it means all the vectors I can this way, is geometrically going to be all the vectors which are in this plane P. Everything is in the plane P. If I take a vector which is outside P, so this is, imagine you have a plane, that's your plane, and I take something outside P, somewhere here. Can I reach the tip of my purple pan using the direction of U and V? That's the plane, the one you guys see, and I am right here. Is there a way I can write the vector that goes from 0 to the tip of my red plane by following the direction of U and V? Yes or no? Okay, I ask, no way. So the only vector that I can reach to following Q and V are the vectors that they have in this plane right there, containing 0, U, and V. So the span of U, V, the span of those two vectors is nothing more than the plane that contains them, is nothing more than a plane, or to be very exact, all vectors on the plane. It means that tip on the plane that contain 0, U, and V. All vectors on the plane. And this plane has a name, and this plane is called, so this plane, which is the span of U and V, the plane is called, okay, the plane is called the plane spanned by U and V. Sometimes we give it a name, and we call the plane spanned by U and V. Okay. So if you have two vectors in R3 and you take every possible linear combination, you're going to get a plane, because there is no way you can get out of the plane when you're taking the linear combination. Now, please ask any questions before I proceed. Okay. But what happened in R2 also can happen in R3. And what do I mean by that? So suppose I give you two vectors. Suppose you have, so you're given the following. V1, let us say, I'm not going to think very hard, and V2 to be 1, 2, 4. And the question is, I want to look at the span of, I am in R3 now, span of V1 and V3. I want to describe this to you geometrically. So back to you, do you think the span is going to be a line? Sorry, is the span going to be a plane? I already gave up my answer. No, exactly. So whenever you have vectors, even if they are two, we don't jump immediately and say it is a plane because I said so in class. You have always asked yourself the questions, are they scalar multiple of each other? Is one the stretch of the other one? Now, if we follow very carefully from here to here, that's you multiply by a half. So it's the same multipliers by a half and by a half. So it means that V2 is nothing more than a half V1. So whenever you have two vectors, you have to be a little bit careful, not always jump a plane. You have to see that, do we have already those two directions that we can use to cover a plane, or we only have one? And in this case, so here V2 equal half V1. So since V2 is half V1, the span in this scenario is just a line. So always, don't think about as idea of direction, you can understand the idea is nothing more than a line, but we have to be careful. We are in R3 now, and it's a line in R3. So we do not confuse, R2 and R3, because every vector here have three components. So my vectors are in R3 because they are a list of three numbers. So that's the idea for two vectors in R3. If they are not scalar multiple of each other, then you can get a plane. If they are scalar multiple of each other, then we will get a line. And so what should be our other concern now is three vectors in R3. So if you have three vectors in R3, and today I'll talk about it, and then there are a lot of ideas when you hit three vectors. So, but let me ask you questions here. Do you think, if I take three vectors in R3, three vectors, and I start combining them just by intuition, do you think I'm gonna get everything in R3 necessarily? What do you think?
I would only say as long as none of the vectors are scalar multiples of each other, then yeah, you can go anywhere.
You're kind of correct, not fully. Not scalar multiple, we need a little bit more. And we're going to study more. I mean, we're going to have a whole section that's going to discuss this idea. We need a little bit more. Same deal, they must have non-zero component, not necessarily. I mean, if I take vectors 1, 0, 0, 0, 1, 0, I will answer that in a second because that will be nice. So is the span equal R3? Some students, they tell me if they have the same direction, absolutely correct. Same direction, forget it. When you span them, you get a line. So the answer is no. Who can give me another scenario where they are not necessarily in the same direction, but the span is not R3 also? So your first answer is absolutely correct. If they are in the same direction, it means they are scalar multiple of each other. Definitely the span is this. So that's scenario number 1. Who can give me another interesting scenario where they are not all three of them like this, but still you don't get all of R3?
It could be a similar situation as that one, but it's only two of them going in the same direction and one is going in the other direction.
Nice. That's nice. That's nice. One like this, one like that. I like that. And this is V3. When I start combining them, yeah, or all in the same plane. Exactly, that's the idea. So yeah, so when I combine those, so if I move in those direction, the only vector I can reach, because this is the same direction. I'm here, I'm not really moving. I'm not changing direction. You're giving me one. So I'm gonna stay within the same plane. Everything outside this plane cannot be reached. Absolutely correct. And then one of your classmates is giving me the following example, all in the same plane. So what does he mean by that? Suppose I take V1, V2, and this example is actually interesting, but imagine you are in R3 here, which is a problem for all of us because, and V3 is, I take the plane that's formed by 0, V1, V2, and my V3 is actually within this plane, right there. They're all three in the same plane, even though it's tilted because you are R3, but all three of them are within the same plane. And then what happened here? If I start adding those vectors, so if I move a little bit in the direction of V1, then a little bit in the direction of V2, then a little bit in the direction of V3, I never leave the plane. The span also is not going to be R3. Okay, so to have R3, we have basically to have this picture. I want my vectors to be very, very different direction. And this is going to trigger the definition that we're going to see very soon. It was called the idea of linearly independent, which tells me that for this to happen, those vectors, none of them should be a combination of the other two. So they have to be very independent of each other. Okay, so at this note, I finished the lecture. Please, you're gonna have a quiz next time. On Wednesday. And because most of you did not do well on the last problem in the previous quiz, the one about solving the system, and I cannot afford that, so you will have a question that has to deal with system. Are you with me? Do you guys hear me?
Yes.
You all hear me. So you're gonna have, I'm telling you already what type of questions I have. So you're gonna have one questions that deal with system. It means I will give you even the echelon form. I'll give you the system. I will give you the echelon form of the matrix because that's not the part I want. I'm gonna ask you solve it. So you have to identify free variable, whatever basic and so on. So you will have a questions about the system. There are other type of questions also I wanna make sure you guys can handle that I will ask you somehow. I'm gonna give you a system that involve like a parameter h, something we've done. I don't know what I'm gonna give you. Now I'm just putting stuff. And I'm gonna ask you question like for which value of h and k the system have, let us say, unique solution or infinitely. So that's the second question I expect you to do because I wanna make sure you guys are doing those. And then definitely a question about span and linear combination. Okay, so your quiz will cover, so please make sure you know that. Make sure you can do one of those, and then span and linear combination, you go over the homework. All right, any questions before I let you go? If anybody has questions, please, you can stay and I can answer any questions you have.
Yes, I have a question.
Sure. You guys can leave. Those who have questions, please stay. Yes, go ahead.
If you have a question where they give you a matrix and a vector, and they expect you to show that the vectors derived from the matrix, I'm trying to figure out how to word this. If you have a vector and a matrix, and they ask you to show that the vector given is a linear combination of the vectors.
I haven't covered this yet.
Oh, okay.
Okay, this will be covered next time.
All right.
All right. So no, wait. My apologies. Give me a second. I mean, I'm trying to refer to the problem I've assigned because sometimes I forget that, okay. So I don't wanna, are you talking about a question like this?
Yes.
Oh, that's not hard. I mean, what here they mean, my apology. Here they mean determine if B is a linear combination of the vectors formed from the columns of the matrix A. You should have asked these questions in class. You know, that's why it means these are the columns. This one, and that one. So the question is, can you write B a linear combination of, let me call this V1, call this V2, and call this V3. So the question is B a linear combination of V1, V2, and V3? Okay, so let us rewrite this question in a term that I am using so far. So here, what are the columns of A? So the columns of A are V1, which is 1, 0, minus 2. V2 is minus 4, 3, 8. And V3 is 2, 5, minus 4. And B is 3, minus 7, minus 3. Oh, sorry. Tell me, when you don't see, tell me we don't see. Okay, and the question is basically, is B a combination of V1, V2, and V3? So let's write this down now correctly. So that's really what the question is. It means, can I find weight? That's really what the problem is about. I get the vector B. So that's really what their question is. So this is 1, 0, minus 2, minus 4, 3, 8, 2, 5, minus 4, 3, minus 7, minus 3. Are you with me?
Yes.
Okay, so now basically we have to solve this. And so you can add those vectors. So what does it mean to solve? These are my unknown. So never lose track. Means can I find those? I don't know. Let's check. So this means that C1 equal to 3. And this is 0 here. 3C2 equal minus 7. And that's minus 2C1 equal minus 3. Okay, so I need to find C1, C2 such that this is equal to that. Okay, so now let's write the augmented matrix. It means I want this component to be equal to that. So basically this is equivalent to solve the following system. C1 3C2. So we're trying to write a lot of things in details because that's the beginning. So you have to understand where everything comes from. Okay. So now I do what we do. We write the augmented to correspond to that. Okay, so let's write the augmented matrix. So the augmented matrix would be 1, minus 4, 2, 3, 0, 3, 5, minus 7, minus 2, 8, minus 4, minus 3. And now we have to solve, okay? Because that's a system, 3 equations, 3 unknowns. You know, a system does not have to have a solution, as you know, so we may or may not have a solution. So we have to solve to see, is it possible to find those weights? Okay, now we solve. Okay, so I go after my leading. I have 1 sitting nicely here, so I do not even touch it. I use it to make this into a 0, so I'm right there, 1, minus 4, 2, and a 3. I have a nice 0 here, I will leave it. And then 2 minus 2, it's a 0. and I multiply this by 2, I will have minus 8 plus 8. Am I right? 0. 2 times 2 minus 4, that's 0. Okay. So definitely we know that there is an issue, right? 2 times
Right.
3 is 6 minus 3, that's a 3. So definitely we have inconsistent system. Which means that the vector B is not a combination of the columns of A. It means of V1, V2, and this is not a combination, or sorry, a linear combination of the columns of A. Okay, but don't let the word columns of A be problematic. The columns of A are nothing more than those vectors. So the columns of A are the vectors 1, 0, minus 2. These are the columns of A. Means this vector, which was minus 4, 3, 8, and this vector, 2, 5, minus 4. So there is no way you can stretch this by a little bit, stretch this, and then hit the vector 3 minus 7 minus 3. So a combination of those will never give you this vector. And geometry was going to happen that although 3 will be in a plane, that this vector will not be in it.
Okay.
All right.
I think if the system was consistent, would we absolutely have to find the value of the weights?
My question will be clear.
Okay.
It means I will tell you, okay, if consistent, find the weight.
All right.
Or I will write, if consistent, write B as a linear combination.
All right.
Okay, so that's how I will phrase my question. So if I wanted to, then I will do that. Okay.
Okay.
Yeah, I read your question, Matteo. Keep going.
Another question is if they ask you to in this linear combination process for solving, if they give you vectors or whatever to make into a linear combination, is it ever a good thing to just not have to write out C1 plus C2 plus C3 and all that and make a system? Is it ever better to just jump straight to the augmented matrix? I mean, if you have the values and the vectors.
I tell you why. My answer will be no. I tell you why no.
Okay.
Because if you jump to the augmented matrix, you don't know what are you doing, and you don't know what you're solving. I mean, because in this class, everything we do will really boils down to solving an augmented matrix. So if you lose track with what are you solving for, you lose the problem. Are you with me?
Yes.
That's what's crucial. That's why in class I spent my time and I've been trying hard to write it this way. Because I want always to remind you that that's what we are looking for. Otherwise, it will become jumble mumble in your head.
Okay.
Because if I ask this question and you reach here, then you forget what are you doing because you don't know what equation you're solving and what you are solving for.
Okay.
That's my answer to that.
All right, I got it.
Okay.
Thank you.
Keep going. Any other questions? Okay. All right, Matteo, the second type of problem is, let me be very clear, crystal clear, because I'm not hiding it. Problem like number 19, for example, that I've assigned as homework, or number 17 in section 1.2. It means here you have an equation in x1 and x2, and there are parameters h and k. And for some parameters, you know, we may have a solution or we may not have a solution. Okay, and so the question would be, what for which h and k, for example, we don't have a solution. For h and k, we have like infinitely many. Matteo, did I answer your question? Yes. Okay. Any other? You guys can ask any question you want.
Excuse me, could you bring back the definition of a span for a moment, please?
Yeah, it's, oh, yeah, I have it. Basically, it's from the book, so I don't make up my own definitions. Here you are.
Thank you. Let me just jot this
Sure,
down.
take your time. Take your time. No problem. No hurry, guys. Anybody else have any questions? You can put them on chat. Paula, Joey, Chris, any questions? What else isn't there?
I'm almost done jotting down.
You're fine. You're fine. No hurry. Joey, any questions?
All right, I got it. Thank you.
Sure, no problem. Any other questions?
None that I can think of.
Okay, I have office hours actually now from 3:30 to 4:30. So if you can think of anything, just drop by, okay?
Okay.
All right, Joey, do you have any other questions? Okay, so I'll end the meeting. Bye, guys.